Let us now talk in more details about the ARM instruction set architecture. The main question is, how do you control a processor? Also, what is actually stored in the memory? In the context of an ARM processor, you will find thumb opcodes. These opcodes are binary coded instructions that will tell the processor which operation to execute. So these operations can be directly translated into a human-readable language, which is called the assembly language. Some can argue that it's not really human-readable, but at least it is not in a binary form. In the context of ARM, you can find different types of assembly instructions, which is actually common in many different processors as well. You will have memory access instructions, you will have arithmetic-logic instructions, control instructions, jump, going through your code, and instruction that can manipulate the control register to reset a flag or to set a flag instead. Let us now review the memory access instructions. Memory access instructions are used to read from and write into the memory. You will find two main instructions that are the LDR, where you want to load the register content with a value coming from a given memory address, and the STR operation, where you store the content of a register into the memory. The syntax usually goes as follows. You have these STR or LDR opcodes that are followed by a conditional bit that you can use to set conditional operation. We'll discuss that in a few minutes. And followed by the register you want to consider and the given address. So for example, in that case, you will load into the register R0 the content currently stored at the address saved into the R1 register plus 8. The memories in the system must support all sizes. I mentioned that we can have word access, half word, and byte level accesses. So we do also have variations of this LDR and STR commands that will be able to get individual access of word, byte, or half word. So this is something to consider once again, depending on what you want to do in your system. Let's now look at the arithmetic-logic instructions. This will be the bulk of the performance of your system, right? Because a microcontroller is here to compute numbers. And those instructions only work between registers, and you can implement arithmetic operation, addition, subtraction, multiplication, and so on and so forth. Logic operations, simply and or Boolean operations. You can have comparison, where you compare, you test if it's equivalent, and so on and so forth, as well as data movements between registers. Here's an example of the syntax with the add operation. So you want to add into R0 the content of R1 and R2. Let us now move to jump instructions. Jump instructions are used to create branches and subroutines. So for instance, the B instruction will simply branch your code to a given label. So you are going to jump from a portion of your code to another one. So typically, you will simply move from a place in your instruction code into another one. And this is all relative to the program counter. So you'll be able to move from X location from the program counter to another one. The BL operation is made for subroutines where you'll be able to jump into a new portion of code and then return back where you were. In order to support this mechanism, you need to store the return address in the link register, and that will be used to bring you back when you're done with your subroutine. So think about it as a function. When you enter into a function, you go to a specific location of your code, and once you're done, you want to go back to where you were. So, and this operation is done by simply restoring the content of the link register with the program counter. As we have seen on most of these instructions, you do have conditional execution and flags in the ARM instructions. So most of the ARM instructions can be made to execute conditionally based on a condition code field. So that was the cond instruction, the cond parameter I just showed you in the previous slides. This is used to improve code density and performance because you will not have specific instruction to test before you operate your instruction. So, for example, if you create this following function where you will compare if the content of R3 is equal to 0 or not. If it is equal to 0, you do not operate this instruction. If it is different than 0, you do perform the addition of R1 and R2 into R0. Instead of creating these 3 instructions, everything can be replaced by this only 2 instruction where you first make the comparison and then you add if it's not equal to 0, and you will end up making your conditional operation. So basically, instead of having these complex branching operations, you can have everything in a more conditional form. There are many accepted conditions in the ARM instructions, such as is it equal, not equal, is it positive or 0, did we get an overflow, is it greater than, less than, and so on and so forth. What does that mean? What does this condition mean? It basically tests the different flags you will find in your status register. So it does not perform an additional operation. It simply looks into the specific flags you add. Those flags can be set by other instructions. That's what we saw in the previous example, where the comparison flag was simply setting flags equal or not equal, and then in your second instruction you just verify what the status of this flag is before you execute the instruction. Let us now review very quickly the equivalence between C and ARM assembly code. In this class, we're not going to use the ARM assembly code because it gets fairly cumbersome to implement a complex system using an assembler. Instead, we're going to use low-level C, but it is very important to understand the direct relationship between your low-level C and the ARM assembly code. Let me give you an example with this if statement that, based on if of a condition, if it is true, I'll do one part of my curly bracket. If it's false, I'll do the other portion. How is that translated into assembly? You first are going to implement a comparison, and depending on the value of this comparison, you will branch to one subroutine or another. Here's a typical pseudocode of what you will end up having in assembler. You compare your condition. If it's not correct, you jump to the false case. Otherwise, you execute the true case, and once you're done, you jump over the false case. So, as you can see, that's a fairly complicated set of instructions to write in assembler, while in fact, writing that in C is very easy. So, this example code, where if A is equal to 7, I just increment a counter, otherwise I decrement it. If I was about to write it in assembler, I would end up with my first comparison followed by my branch, an addition that is conditional, jumping over the false case. The false case will be the subtraction, it is conditional as well, and so on and so forth. So with these 2 lines, very easy pieces of C code, I can replace a more complex subroutine. Now, you do replace this complex subroutine when you write your code, but it's effectively translated into this kind of solution. So you must keep in mind that any bad C code will end up with a bad assembly code. So you need to take a lot of attention in your C code and understanding what you do.